Here we are, it's the physics video lecture. Physics 2A video lecture 13. And let me start off talking about what we're going to do today. Not that much time left in the semester, but there's some very important topics. Then I have some nice demonstrations for us later as well. So we're going to talk about chapter 12, and I want to go straight to the entropy concept. So here's how the logic of this goes. We just finished talking about heat transfer. So heat transfer mechanisms, conduction, convection, and radiation. And in heat transfer, it's always energy moving from the higher to the lower temperature, T hot and T cold. That's the direction that the energy flows. But in each of these mechanisms, we can also analyze this on an atomic level or on molecular level. And then we had motion, because we knew that the higher temperature corresponds to faster motion, say in a gas, or more highly agitated molecules in a solid. And the lower temperature, lower speed motion, less agitation. So we could also have imagined that we had molecular motion. Let me go ahead and write here molecular motion. And we've got a candle here and it's heating up this metal bar. And the atoms here are moving very rapidly. Here they're moving slower. And the rapid motion eventually moves from the higher to the lower temperature. Okay, so we've got TH over here, TC here, and we've somehow got the heat progressing through the metal bar. Okay, so that's the idea of the heat transfer. And there's a concept that goes with it, because we could also say on this side where it's agitated, we have disorder, and on this side where it's cold, we have more order. So we're going to think about the order and disorder at the molecular scale. So order versus disorder. And the nice way to, we've got that block of ice. Every molecule is in place, so to speak. So there's ice, that's order. Now what would disorder be? Could be the liquid, could even be the gas. So how do I draw the gas? There's the balloon with the particles in there, so we have solid. And on the way to the gas, we would have liquid. And we would have gas. So order to disorder. Okay. And the heat flows from the higher to the lower temperature. So if we just focus on this side, it may be ice now, but in time it's going to increase in temperature and increase its disorder. Okay. So order versus disorder also on the molecular scale or the molecular view. Now, there's a new concept that goes with that called entropy. And this is at the end of chapter 12. I'm starting at the end of the chapter. Sometimes I do that. This is the important concept, and it's best discussed right after you've talked about heat transfer. That's why I'm doing this right now. So entropy is a measure of the disorder, of molecular disorder. I'll just write disorder. And now let's go ahead and introduce a formal expression for the entropy. It's going to immediately tie into the heat transfer. Yeah, so this is the end of chapter 12. So entropy, change of entropy. We're always just going to talk about its change. Delta S, actually before we write that expression down, So we're going to imagine that we've got this object here into which energy flows. So energy is flowing into our object, and this object has a certain temperature. We know the temperature is going to increase. Unless it's ice, it could stay the same and melt, but the disorder is definitely going to increase when we add this thermal energy to our object here. So now this change of entropy, delta S, is defined as Q over T. I could say delta Q, but I'm just going to stick with Q, okay? And we have to say, well, what are the units here? The units are joules per Kelvin. So delta S units, joules per Kelvin. So that's a hint that we always have to use Kelvin to degrees Kelvin with this expression. So delta S is Q over T, where T is equal to T measured on the absolute temperature scale. Okay, so now let's give an example of this. You can say this is the energy that flowed in divided by the temperature at which it happened. Okay. So I'll put a box around here, and then I'll give an example. Entropy change for melting ice. Okay, so here this is going to be a block of ice, and we're going to add some heat to it and melt it. Then we're going to have delta S is equal to Q over T. But remember, we had a heat associated with melting ice. That was the mass times the latent heat of fusion, mass times the latent heat of fusion divided by the temperature. And if we wanted to evaluate that, since it was for ice, we would have a mass latent heat of fusion of water divided by 0 degrees. What can we divide by 0 degrees Celsius? No, we have to use the Kelvin. So divided by 273 Kelvin. So given a certain amount of mass, certain mass, then we would plug our numbers in and we get so and so much change of entropy in joules per Kelvin. Okay, so these applications are easy if the temperature remains constant. If the temperature itself is changing, then you have to actually do an integral, which we're not doing in this class. So we'll just keep them simple when the temperature is constant. So that's the entropy change for melting ice. Now I have to add some rules to this change of entropy. I'll just call this entropy rules. And the first one is delta S is negative when energy leaves a body. And then we have delta S is positive when energy enters a body. Energy enters a body. Okay. So for example, if we had this entropy change for melting the ice, this would have been a positive number. But if we had the entropy change for the ice freezing, okay, then we would have had a negative number. Because then the energy would be leaving the water, it's turning into ice. So these rules are very important. At least I said them, can barely read them there, but I'm not going to rewrite them. Delta S is negative when energy leaves. Delta S is positive when energy enters a body. So now here's my all-time important example. And then we can get to what the actual meaning of this entropy is, why it's so significant. So now the important example, I'll even write important example. What we're going to imagine now is we have an isolated system for us, an isolated system, we take a couple things, put them in an ice chest, close the lid, right? Put them in a cooler, close the lid. So there's our isolated system, and in this case, we're going to put a hot object and a cold object together in this box, and we know the direction Q is going to flow. Eventually, of course, they'll equalize in temperature, but just ask what's happening immediately, okay? Immediately, these two are in contact and energy is flowing from the hot to the cold. So the delta S total of this process is delta S of the H side plus delta S of the C of the colder side. And I'm going to apply these rules right here. Okay. Here we go. So delta S total is equal to, now from our definition, since it's leaving the hot side, we could say it's minus Q over TH. That's this one here. And I'm going to put an absolute value just to make sure we're talking about minus so and so many joules over TH. The same energy is entering the cold side, so that's plus the same Q over T sub C. So that's the total entropy in a process that's been isolated, where just the nature takes its course. Energy flows from hot to cold. Let's go ahead and evaluate this. You see we have a common absolute value of Q, so that's positive, and then we'll have 1 over TC minus 1 over TH. Okay, we could just leave it at that. Let me just rationalize this. So we will have TH minus TC divided by the product TH TC. Okay. Now what's the punchline here? The punchline is that this is always positive, right? TH is always greater than TC. This means higher temperature, lower temperature. So this minus this is always positive. Everything else in here is positive because these are all kelvins. Therefore, this is greater than 0. And what we had was, we just analyzed the most basic process, energy flowing from hot to cold, and we found that the total entropy is always greater than 0. That's a law of nature, okay? That's a law of nature. It says that the total entropy of an isolated system always increases. And what's so important about it is, it's just a formal statement. It has more generality, but it's a formal statement of the fact that energy always flows from hot to cold. And we'll agree, this is a law of nature too, okay? So this entropy law is this law of nature, okay? Things flow from hot to cold. They go from ordered to disordered, is another way to look at this. Okay, so this is the all-time example. One of the homework problems I'm going to assign talks about energy flowing from the earth to the, from the sun to the earth. And really, you're just going to do this calculation, except they're going to give you some high sun temperature and some earth temperature, okay? So a very important example that you can totally trust this law because this is what it means. So let me write this down here. I'm going to showcase it. This is called the second law of thermodynamics. Second law of thermodynamics. Second law of thermodynamics. The entropy of an isolated system increases. energy of an isolated system increases, and if you want to get particular example, or it stays the same, okay? Increases or it stays the same. If I put two objects at the same temperature in here and close the lid, then nothing changes, okay? So it increases or stays the same, and that is just formally the same as thermal energy flowing from hot to cold. Yeah, so if this law were to be violated, it would be possible for thermal energy to flow from cold to hot in an isolated system. This is something you're never going to experience. Let me give a different example. Imagine I have this thing here in ice on one end and boiling water on the other, okay? It's ice on one end, boiling water on the other, and therefore the temperature is flowing here and eventually melting the ice, okay? You would not have the ice on this end and yet heat flowing out in this direction and ice getting colder and colder, okay? Many examples of that type, but they all go back to the idea that the energy flows from hot to cold and the disorder is increasing. Good. So I've made my point 5 times now, but this is a really important law. It's the formalization of the heat transfer and many other things as well. So it plays a role in chemistry, and where we're going to use it is when we start talking about heat engines. So the big goal of this chapter was actually not to talk too much about entropy, but we're going to use this law later on. So I'm assigning 2 or 3 problems from this homework, just to make sure we understand what's going on here with the entropy. And then we're going to move on to talk about heat engines, and I brought some demonstrations of heat engines to make a couple points as well. Good. Let's see how we're doing for time today. All right. Not going to go too long today, but still have a fair amount to talk about. Okay, so far so good. That was entropy, and now we're going to talk about heat engines and why they're so important. This is a topic, comes at the end of the semester. We're running out of time, but we definitely have to learn this, and it's not a difficult topic, but for our entire civilization, the heat engines are pretty important. Good. So the next part of chapter 12, we're going to talk about heat engines. And I'm going to demonstrate some heat engines and then analyze them. But what is this heat engine concept? The idea is work from heat. Work from heat. Okay, let's recall one more thing before we look at our demonstrations. I like to talk about the mechanical equivalent of heat in this connection. Mechanical equivalent of heat, who remembers what that is? There's a definition. 1 calorie equals 4,186 joules. This is the capital C, food calorie. This is work, mechanical work. This is the stair climb, okay? Food calorie and the stair climb. Now, up until now, we can prove this and demonstrate it in this direction. That is to say, we can do some work and generate friction and generate heat, okay? If you do it carefully, you can get this exact equation. But knowing that there's so much heat, say heat of combustion in coal and gasoline, etc., what do we have to do to go from that thermal energy here and get useful work out of it? Okay, so this direction of the arrow is friction. This direction here, I'm just going to put question mark. Of course, the answer to that question mark is we have to devise some kind of heat engine. Okay, so if we could just take the potential thermal energy here and somehow turn it into useful work. That would be our goal. Okay, let's have a look at these demonstration objects. These two here are called Christmas pyramids. Germany, Austria, etc. That's where they come from, Europe. And they are a heat engine demonstration. Actually, you have the wise men here and you have the nativity scene. And this is a turbine, it's a propeller. So I'm going to light these candles and see what happens. Okay. What do you know? Okay, these aren't butter candles, which are my favorite candles, but still, this is a functioning heat engine. Because we have fuel, the wax is fuel, we're releasing it into thermal energy. We have convection, air currents are rising, and then they're going through the turbine and spinning this thing around, and that's useful work. Okay, let's try this one. Actually, this one I haven't run for a long time. I can't even claim that it's gonna run, but let's give it a shot. I think we have some success here too. Okay, careful. Alrighty. This one is tearing it up. This one needs a little help. Okay. Now there's one more really important effect that I have to demonstrate. As fast as this one is moving, there's a chimney effect. Now, I can avoid burning this house down here. Let's see. I'm going to fashion a chimney. Wish me luck on this. Okay, I'm going to fashion a chimney and put it on this slowpoke. And as you'll see, it is speeding up. I'd say it's speeding up significantly. The chimney is an important aspect of the heat engine. Okay, fantastic. Now on this one here, I can get it to speed up even more, because now that's really going to go to town. Okay, proof of concept, fantastic. So the chimney effect is crucial to really getting some efficiency out of this thing. Okay. I'm going to turn these off. Okay, hope the smoke alarm doesn't go. Yeah, wish me luck on that too. Okay, so the candle's out, Christmas pyramid comes to a stop. So this is a heat engine. You saw we had heat and it was locked up, thermal energy in the candle there, heat of combustion. So we burn that, get some heat, and we actually got the useful work, namely the thing spinning around. By the way, the turbine is the modern form of a heat engine actually. Here I have a steam engine replica that works. So I'm going to demonstrate this as well. It has a boiler, a very small piston and cylinder, and this thing will spin that way, and with any luck we'll get a light to go on. This model here kind of demonstrates the reciprocating motion and the circular motion. So you can turn something circular motion here, and there's the piston moving back and forth in a cylinder. So that's what's going on inside of this model. So yeah, the last thing I'm going to do is fire up this model here. And see if we can get this fuel. So I have some solid fuel here. It does, you know, I brought my torch. If this doesn't catch fire in a second, I'm gonna get impatient. There we go. Okay, so this needs a little patience, but this will be a functioning steam engine. And we'll fire this thing up here. So I'm going to draw a couple of things while I'm at it. So our examples are, first of all, the Christmas pyramid. Not sure why it's called a pyramid, but this is what it's called. You can look this up online. You'll see some much more impressive ones than these little heirlooms. Okay. Yeah, so the Christmas pyramid, we have this turbine here. We have a long axle. Down here we have candles burning. And we have some kind of machine here that is actually functioning. Okay. And our figures were being carried around in a circle. Okay. So the physics here is we have wax, and that is the fuel. It has a certain heat of combustion. We burn that fuel, and we get heat here and an air current going up. One important point is that it's hotter here and colder up here. Obviously, right? It's hotter by the flame and colder up there. So that's the Christmas pyramid. Now I hear this thing making some noise, and we're probably ready to rip. There we go. Now you guys know what you want for Christmas. Fantastic. I think I'll hold this in front of the camera a little bit closer. Okay, I'm assuming this makes it visible. Steam engine, firebox. Okay. So how do you turn this thing off? Yeah, that's the only way to turn it off. So, very functional. And this thing also has to have a schematic diagram and first of all, just a picture. So we have the Christmas pyramid, and the second example is the steam engine. And for the steam engine, let's go ahead and just draw that it has a boiler. It's got a window in the side, in the end, and there's water inside. So water, how about some blue for the water? Okay. It's got a boiler, there's water inside. We've got some fire underneath. We've got a connection to a cylinder with a piston inside, connecting rod to a flywheel, okay? And very crucial is that there has to be a valve that releases steam, okay? So that's the steam engine, that's the Christmas pyramid. I'm going to talk more about the actual functioning of these, but at this point you see you have steam in here, pressure inside the cylinder, it's pushing the piston forward. That's where the work comes in. Pushing the piston forward, we've got the same idea here, okay? And turning the wheel. The thing is, if you want the piston to push backwards again, then there's all this pressure there, it won't work. You have to release the pressure inside, and so the valve is very important, releases the excess pressure. Okay, those are the two examples that we're going to analyze. And I may save the analysis. No, we'll do some analysis before we finish up. I'll save the technical analysis for the next hour. Right now we'll do a little more of this. Work from heat. Okay. Main thing I wanted to really demonstrate these things to you. And all of the key properties have actually been seen. That chimney effect was very important as well. So let's analyze the Christmas pyramid a little bit more. Actually, all of the things are in place except for the chimney effect. So yeah, you know, you guys make a better picture than I made here. I'll make a better one in a second too for the steam engine. If you have a better picture of this, the point is we got the fuel here, the high temperature, the low temperature. The chimney was crucial for really spreading out the high and the low temperature. Okay, that's why it made the Christmas pyramid so much more effective. If there were just hot air above and beneath and everywhere else, you wouldn't get that airflow. So to get the airflow, you need a real separation of high and low temperature. That's what the chimney did. The steam engine has a real separation of high and low temperature because the boiler temperature is very high. The air outside where the valve releases the steam to the air outside is much lower temperature. So we again have a high and low temperature separation. So I'll put this as an important point. For a heat engine to function, you have to have higher and lower temperature regimes very well separated. Separation of TH and TC regions. So we have that for both heat engines. And yeah, what else is a heat engine before we go on? So heat engine examples, I've given you this turbine style. I've got the old-fashioned steam engine. Your car engine, of course, if it's burning gasoline, it's a heat engine. So for power generation, for transportation, these things are very, very important. And what we're going to do is apply just our basic physical principles to get a very deep analysis, useful analysis. Okay. I think that we're going to leave it at that. And next time, I'm going to start with these diagrams and then do a heat engine diagram and continue its analysis. That's what I consider most important of chapter 12, by the way. So we're really doing entropy and then the heat engines and the analysis of the heat engine. Good. Let me write down what the homework problems were that I thought we would do. This is from chapter 12, and I have here 48A and 53. Maybe I could find one more good one for you. These are both of entropy. Get the one with the sun. Yeah, let's just look at 54 as well. Good. There you have it. So, as always, take good notes. And I've seen so many good notes, just keep that up. And what about these? So, this lecture 13, 14, and 15 this week, those will all be due on Friday. Okay, good. See you next time.